start with example 3.1.3. And this is going to be what we call a wireframe model. And we'll start in R2. A subfield of computer science, I guess we call it. It's a very, very powerful subfield, actually. There's entire GPUs constructed on this concept, right? Is known as computer graphics. And we're actually going to go ahead and start with the simplest case of computer graphics. Could you guess why? Because if you understand this one, then the other one's not too bad, right? So 2D computer graphics, which generates models for two-dimensional shapes that can be visualized on a display. And this leads to what we call animation, right? So animation is the dynamic. Simple graphics are what we call like the static, right? So we'll begin with a wireframe model. Consisting of two ideas. Let me just say this. Consisting of what we call a vertex matrix and an edge table. For now, we're going to talk about undirected edges. Physicists like directed edges, and I'm cool with that. For the standpoint of physics. Can I switch? Which one's which?
Right one.
I want this one, right? So we will go back to a very early example that we did in lesson 2 or 3, I forget. And it was also hinted at on your test. So let's recall our vertices from a previous example. V1 we said was 0, 0. V2 we said was -1, 1. Anybody remember what V3 was? 2, 1. Awesome. Oh, sorry about that. Thank you so much, sir. The vertex matrix associated with this model is, could you guess what V is? What's the first column of V? 0, 0. What's the second column of V? -1, 1. What's the third column of V? This one right here is called the entry by entry definition of that matrix, because how did I specify the entire matrix? Entry by entry. I didn't specify column by column. That's called the column partition version, and we'll get there. We're going to get there eventually. So this is now what we call a 2 by 3. If I were to draw this, right now, do you remember what we imposed about each vertice or vertex? It's just a point. But then we said to ourselves, hey, sometimes we actually don't want it to be just a point. What else do we want it to be? connected. And this is where an additional piece of information that we would need to specify is called an edge table. We'll go ahead and say let's talk about the edge number. And then for now, we'll go ahead and call these start vertex and end vertex, but it doesn't really matter if this is undirected. So this is where physicists get a little bit finicky because they always want that little arrow at the end of their connectors, right? So let's talk, well, in this case, how many edges would you expect there to be? 3. Let's talk about the first edge, and maybe we said the first edge is the one that connects V1 and V2. And perhaps we say, let's start at the one that's smaller and go with the one that's bigger. Or, if you didn't want to track the fact that these are vectors, you could just say start at vertex 1, end at vertex 2. Could you guess what number 2 was? Edge 2? Yeah, perhaps we said edge 2 connects vertex 2 to vertex 3. What about the next one? Yep. Now, here's a question for you. If I were to want to manipulate this matrix, which piece of information, if I wanted to turn this around without changing connectivity, which piece of information would I change? Would I change this stuff or that stuff? If I wanted to move this around, like turn it, expand it, etc. I'd change the entries of the matrix. I wouldn't touch this because the connectivity doesn't change, right? What type of operation would change the connectivity in this particular thing? If I cut it or broke it, right? So then the idea would be, as long as I have the connectivity, I can actually now do a lot of stuff with this particular setup that makes this look like it's moving all around the page, right? I could make it expand, I could make it contract, and all I would have to do is do calculations on these particular entries, right? This stuff doesn't change, but this tracks how we're connecting that particular piece of information.